Hi, my name is Vinay Gupta. I am running my project assignment for machine learning foundations for product managers. This project is about the combined cycle power plant to create a machine learning model. What we've been given is a data set with four input variables and one output variable. It has 9,568 hourly observations. So let's quickly analyze what we have. Given the problem is about predicting a numerical output from a set of input variables, this will be a good fit for a regression model. And given we have more than one variable, we would like to go in with a multiple regression model. Interpretability is super important given this is a numerical output for a set of readings. And given this is a numerical interpretation, we can look at a parametric algorithm. Uh, Now, for an output, uh, our error or our cost function will be SSE. It is simple and commonly used and normalizes any outliers. It's essentially a sum of square of difference for each reading against the actual reading. So how will we look at the algorithm? So let's look at what do we have here. We have here a power plant giving some power with some variables in place. So this will have a combination of features. Now, for the power plant to work efficiently, the motor needs to be efficient. The ability for it to be optimally warm and be able to continue to also lose heat with ease. Therefore, the temperature would be one very important feature to keep as an input. Also related would be the relative humidity as a variable would be important to also keep, given this will determine how fast can the pump lose heat. More humid weather at high temperature will make it difficult to lose heat and hence efficiently produce power or be inefficient and vice versa, which then leaves ambient pressure and exhaust vacuum as two extra variables. Both are similar variables as they talk about pressure conditions of pump. We can hence consider three algorithms with the following input variables or features. Algorithm one will have the temperature, the ambient pressure, and the relative humidity. Algorithm two will have the temperature, ambient pressure, exact exhaust vacuum as a three inputs. Algorithm 3 will have all the inputs. Algorithm 4, I thought I'll create one just with one input. I thought the atmospheric temperature has a big impact. Let's see how it behaves to it, just that. The data set has 9,568 variables. What I did is divided it into three sets. Training set of 6698 where we'll run all the variables, we will run all the algorithms and see which one is the best based on our minimum cost function. Validate with the 20% data set of roughly 1900 readings and then test it out with 10% readings of 956. I'm going to use Excel to run my four algorithms, come up with a final model, test the data. I'll also try and talk a bit about the regularization penalty and how to calculate that. Now, it may not be possible for me to do it in Excel, but yeah, I'll try and see what I can do. So I've already set it up in Excel. I've set up the algorithm. I've set up the model just for the sake of time. So it's just run the output for regression. As we can see, the significance F is almost zero. So this is significant for us to talk about. A brilliant R square of 0.92 means very high correlation. Standard error, the way Excel calculates is it doesn't do a square, it does a square root. So we just square it up to come up with our SSE, which is 22.229 from algorithm 1. Similarly, for algorithm 2, it is 223.65. Algorithm 3, 20.17. Algorithm 4, 29.13645. So we can see clearly algorithm 3 with all the variables has the best SSE. So I've copied all the SSEs here. A3 is the best SSE. Then I ran the same model on the validation test to come up with SSE or a cost a figure of 22.86 and a test figure 20.52. So kind of almost similar, validates nicely and comes out very nicely. So I copied the weights of the model. Where do we find them? We find them over here. So it's my A3 model. These are the weights. Also, just to quickly show you how this is plotting up nicely, you look at each variable against the power output. So there's a nice correlation for the temperature, and then yeah, others are a little bit scattered, but then there's a little tight fit on how the line is kind of going in. The negative slope, a negative slope, positive slope, uh, kind of adjusted negative slope here. Yeah, so these are our W's. If we add them up, this is what we get. Uh, to create a regularization or a penalty, we need to also select a lambda and add it to our cost function. So the way it goes is you just do lambda. You multiply it with let's say the minus 2.33234 I get over there. So yeah, you play around with different lambdas to come up with different SSE, and then you do a reverse calculation of your weights. So you're going to replace this SSE for each value of output, and then for each value of output, you come back again with W1, W2, W3, W4. It's backtracking. Once you do the backtracking, you come back with the weights. Then you again use this regression model in Excel to come back with a cost function and see how close you are, or how better your cost function is getting. There's a kind of an iterative or a regression process. You run it again and again to optimize it. So yeah, this is my kind of output. My recommended algorithm is we use all the variables to come up with our output, and that's the best fit model. And when we're using a multiple regression model. Thank you very much, guys.